Hey guys, today we're going to be doing a very simple statics problem. We're going to be doing a simple truss problem via the method of joints. And it's probably something you're familiar with from your textbook. However, we're going to do it in a different way. We're going to use a little bit of linear algebra to systematize the process, speed it up, and make harder problems that you'd normally solve by hand. We're going to use Matlab to solve them. So this is going to be a nice trick for your homework, especially if you are at a point where you're taking a class like a physics class or a statics class where you need to solve some longer or larger, I should say, some larger systems of linear equations, and you have a bunch of unknowns and you want to keep track of everything. This is definitely a nice method to employ. So the problem reads, determine the force in each member of the truss shown below and indicate whether the members are in tension or compression. We have two sides given, each 3 meters, and then we have a force and an angle given. And right now our aim is to find the unknown forces in each member, as the problem suggested. So we're going to start with joint B because we already have a force, a known force on joint B. So what we want to find is the unknown force, which is FBC. We're going to draw the free body diagram, and in the free body diagram we have the force that's given acting in the positive x direction, and then we have another force FBA acting in the negative y direction, and then we have the force FBC, which has both x and y components. So we're going to write the equilibrium equations in terms of both the force in the components of x and the components of y. So starting for joint B, we're going to write the summation symbol and then F subscript x, or we can just say Fx equals 0. And then we can also say that that's equal to 700 newtons, which is the given force, minus FBC times sine 45. Then for Fy, we write that summation symbol Fy is equal to 0, and we have FBC cosine 45 degrees minus FBA is equal to 0. And those are the equations that we need to write down for joint B. And then we move on to joint C, and we're going to start by writing the free body diagram. And we have FBC, which has an x and y component, and then we have a reaction force at CY, which is acting in the positive y direction, and then a force FCA, which is acting in the negative x direction. So for the equations of equilibrium for this joint, we're going to write for Fx is equal to 0. We're going to write negative FCA plus FBC cosine 45 degrees is equal to 0. And then for Fy, we're going to write that the reaction CY minus FBC times sine 45 degrees is equal to 0. Okay, and then we move on to joint A. And we're going to write the free body diagram first before we write our equations. And we have a force FBA acting in the positive y direction. Remember when we wrote FBA, in joint B, in the free body diagram of joint B, we wrote it acting in the negative y direction. We wrote that because it's going away from the joint. Whereas remember, if you look at FBC, where's FBC going? FBC is going towards the joint. Okay, so keep note of how you're drawing your free body diagrams when you're doing problems like this. So we said that at joint A, we're writing FBA is acting in the positive y direction, and then we have FCA acting in the positive x direction, but we have reactions at the supports. So the support AY, we have a force acting in the negative y direction, and then for AX, it's acting in the negative x direction. So again, we can write the equations of equilibrium, and we can write Fx is equal to 0, and we can write FCA minus AX is equal to 0, and then for the sum of the components Fy, we can write that the summation of Fy is equal to 0, and we can say FBA minus AY is equal to 0. And then we have all of our equations written. So we have 6 equations, and we have 6 unknowns. And here's the part where we're going to throw it into Matlab, guys. So this is a simple problem, but if you have a more advanced problem with a lot more, if you have a lot more variables and you have a lot of things that you need to keep track of, then this will really help you out. But let's do this in the simplest case first. So what we want to do right now is we're going to take advantage of the matrix equation, and we're going to write AX is equal to B, and x is equal to the inverse of matrix A times B. Okay, so we're gonna start by writing a column vector, and we're gonna name that x, and we're gonna put all our unknown variables in there. So we're gonna go in order. So in order of appearance in the equations. So we start with FBC, and then FBA, FCA, CY, AX, then AY. You're gonna write that in a column vector. Okay. Then for the right side of our equilibrium equations, we're going to take that and we're going to put that into another column vector, and we're going to call it B, and we're going to write that equal to x. So we're going to have A multiplied by x, but we're just writing x and B first, okay? So B is going to be on the right side of an equal sign of x, okay? And we're going to have negative 700 as the first entry in the column vector, and then the rest are just going to be 0, okay? So we're going to have 5 zeros after that. But we have 700 written there because we have a positive 700 newtons on the left side of the first equation, okay? Okay, and then now we're going to combine column vectors for each variable, corresponding to each variable. We're going to combine them into a larger matrix called matrix A. So we're going to start with FBC. So in the first equation, we have FBC is multiplied, FBC is multiplied by negative sine of 45 degrees, okay? So you see that in the first entry, in the first row of the first column, we have negative 0.707. That's just sine of 45, okay? And then we go down, we have the same thing. We have cosine of 45 degrees for FBC, and then we're going to write 0.707. Then we have another 0.707 in the third equation, negative 0.707 in the fourth one, and then we have 2 zeros for the last 2 equations in terms of FBC. Okay, and then we keep going down the list. So we have FBA. Is FBA in the first equation? No, so it gets a 0. Is it in the second equation? Yeah. So we give it a -1, okay? And then for the third, fourth, and fifth, it's not in there, so we don't give it a value, we give it 0. And then for the last equation, we have FBA is multiplied by +1. Okay, now FBC, okay? FBC is our third entry in column X, okay? So we're going to look at the column, the third column in matrix A, okay? And we're going to fill that up with the values for FCA. And in the first 2 equations, if you look at the equations for joint B that we wrote, FCA doesn't appear, okay? So we're just going to write zeros, okay? But in the third equation, we have -1 for FCA, okay? Then a 0 for the next one. And then for the fifth equation, we have a 1. We're going to write a 1 for FCA. And then 0 for the sixth equation. FCA isn't there. Likewise, for AX, it appears once, and it's in the fifth equation. And we're going to write AX. We're going to give it a -1 in the fifth column, and we're going to write it in the fifth entry of the fifth column. We're going to give a -1. And then for AY, we have that in the sixth column of matrix A, and it gets a -1 in the sixth entry. So bear with me with this this new graphics tablet that I have. My handwriting is not the best with it. I'm still getting used to it. But we'll show you guys on Matlab how to enter these values and solve for your unknowns. Okay, so we've got Matlab open here, and we're going to start by making a new variable. We're going to call it A, and that's going to represent our matrix A, and we're going to input the values. So say for the first column, you can write your values separated by spaces, and then you can hit a semicolon, and then after you write that semicolon, you can start on the next column, and then you have a semicolon, and that takes you to start inputting for the next column after that. Then when that's over, you close the brackets, and you just hit another semicolon so that you can suppress the output. Then we're going to enter B the same way, okay? We're going to make another variable, we're going to call it B, and then you're going to input the values for your column vector B, all right? And then we're going to make another variable, and we're going to call it X, and then we're going to write X is equal to, and then your variable A, and then your /, and then B, and then you're going to hit run, and then that's going to give you your values, okay? Okay, and now we've finished the problem. We can say that FBC is equal to 990 newtons, FBA is equal to 700 newtons, and the same for FCA, CY, AX, and AY, okay? And then it also asked us to determine whether the members are in compression or their in tension. So to do that, we look at our free body diagrams, okay? So when we made these free body diagrams, we assumed that joint B was under compression because we drew the force FBC going towards the joint, And then we also assumed that the force FBA and the force of FCA, we drew those guys on the free body diagrams. We drew them going away from the joints. So we're saying we assumed that they were in tension. Okay, so we would know if they weren't actually in tension and joint B wasn't in compression or under compression, then we wouldn't have all positive values for at the end. So we would know, okay, we got something wrong in our free body diagrams because some of these are negative. So since they're all positive, that's it for this problem. So I hope this was helpful. So you guys can take this, you can take this basic procedure of setting up your problems and then putting them in matrix form and then inputting them to Matlab. You can take it for, this is like a super simple case, probably like the simplest structural analysis problem that you'll get in a statics class or like a physics class. Is like the easiest kind. But you'll have all the other ones that you'll solve are basically just setting up a system of linear equations. As you know, if you're taking one of these classes, then you already know that. But maybe you don't necessarily know how to put it into a matrix form like this and then just solve it with a computer to make sure you're right or something. So it's just a really good way of keeping track of all your variables. And if you do it in a systematic way, you can't go wrong and you'll get your problems right every time.